Fourier series are a lot like transform methods. The point of them is to solve a set of problems. And the problems that we're going to encounter are going to involve partial differential equations. Okay? So just like when we were learning Laplace transforms, we need to sort of work out what these things are and how to use them, and then we'll apply them to some problem. But we really need to know sort of what they are. All right. So let me give you an example here. This is just off GeoGebra. I've just stolen this. And they've plotted a function, but let's actually just make that function even easier. Let's just, I'll just adjust this. Okay? Now, what do you notice about that function? What can you tell me about it on a Wednesday morning in week 8? What are some properties of that function, just by looking at it? How would you describe it to a friend?
For one, it's periodic.
Mm-hmm. So what does periodic mean? I've forgotten.
Periodic means that it repeats itself every wavelength across.
Yep.
And it also appears to be linear at a lot of places.
Well, parts of it are, yeah. What else can you tell me? Okay, we'll pass the mic around. Okay. What else can people tell me about this graph and this function? So it repeats. What else? If you were describing this to John Pork, how would you describe this fabulous function? It repeats. Good morning. How would you describe this function on first impressions? Yeah, that's the other thing. There's some jumps, right? So parts of it are connected and continuous, but there are other parts that are not. Okay? So the main important thing there, though, is the property that you said before, which was the periodic, right? So the way I remember periodic functions is you basically copy-paste, right? So this part's in blue because, you know, if you copy that, move it and paste it, and move it and paste it, and move it and paste it, and move it and paste it, you get this repetition, right? Okay, so we're going to do something a bit radical today. We're going to approximate this graph, which actually is a very simple graph, with continuous functions. How do you do that? How do you approximate a discontinuous thing with a continuous, you know, even smooth differentiable function or curve? How would you do that? Okay. Well, I'm glad you asked, and it's got something to do with the cosine function and the sine function. Now, what do we also notice about cosine and sine? What properties do these functions have? What are some of the properties of the cosine function and the sine function? And I'm not talking like calculus or derivatives or anything.
Periodic.
Oh yeah. Okay. So they're periodic as well. Okay. So cosine, you know, it looks like this, right? Sine is just a shifted cosine function. Now, there's a guy called Fourier, a Frenchman. He realized, or at least he was one of the first people to be credited and write about this, is that you can use cosine and sine functions to do many, many, many important things. Okay? In particular, if you add cosine functions together and or you add sine functions together, you can approximate curves pretty well. Let me show you what I mean. Okay? Let me show you what I mean. Okay. So here's a Fourier series. It's just that black horizontal line. Does that look like a good approximation? Not really. But it's sort of averaging the function out, isn't it? Right? Sort of in the middle of the function. Okay. So what happens if we add an extra term into this approximation? So here we've got one term. Let's put in another one. Okay. So this has taken the function and added in that horizontal function and added in a cosine or a sine function. I'm not going to tell you which one, right? What does it look like from the graph? Cosine or sine? Sine. Okay. So does that look like a slightly better fit? Bit better? Not great, right? What happens if we add another one in? So let's do something with another sine function. Oh. Does that look a bit better approximation? Okay, what happens if we keep doing this? But you can see up here it's not a very good fit, right? But over here and here it's a pretty good fit. Now would you agree that's a nice smooth curve, the black one? Okay, let's go a bit more. So what we're doing there is just adding sine functions together to fit this crazy sine series to a really simple curve. Okay? That's freaking amazing. Right? You can just add sines and get this sort of periodic odd function. It's an odd function between -1 and +1, right? Now, you can also do this with cosine functions. Hello. Greetings of the day. You can also do this with cosine functions, right? Let me show you, see if I can do another one, right? Let's go here. Shall I do that? Let's try that. It's not going to give me what I want. So let me try this one. What can I try? Let's try this one. I'll just refresh. All right. So, yeah, that'll do. Okay. So now we're in a world where, is it still periodic? Does this graph repeat? Yep. It's also odd for that blue part, right? It's an odd function for the blue part. So in this case, this looks like, I think you might call this a sawtooth wave or part of a sawtooth wave or something like that. What you can do is you can use cosine and just add lots of cosine functions together to wrap around that curve. Now, notice this curve is continuous. There's no jumps, but you can still use Fourier series. So let's have a look. Okay, that's the first approximation. Again, it looks like sort of an average, right? It's sort of cutting the graph in half, really. Is it a good approximation? Well, near some points it is, but overall probably not, right? So what happens if we add a few more cosines into our mix? Oh, that looks like the cosine function right there. Yeah, plus or minus some scaling or shifting, right? Look, I can't even tell the difference now between the black curve and the original curve. Can you? Right? So think about, maybe the Fourier series, when we learned about them, you can think of it as a wire or a piece of string and you're wrapping the wire around a curve. That's one way to look at it, right? That's one way to look at it. So what are these Fourier series? Okay. Wow, that's a really good fit. Even that's like pretty good, right? One term. Okay. So let's have a look at what, oh, that's nice. High distinction for you, Zach. Yeah, so let's have a look at Fourier series. All right. So the main motivation here for Fourier series is that we're going to use them to solve partial differential equations, which is what we do in, as the last topic, maybe in week 10. Okay, so the motivation, good morning, is to solve partial differential equations. So we'll look at some partial differential equations like the heat equation, so you have the flow of heat. We'll look at the wave equation, which is the movement of waves, and maybe a few other ones as well, but they're the main ones. Okay? All right, so you've got a function and it's periodic. Now, the way that we describe the length of the period is twice times some number, okay? Because we want half of that period to put into our formulae, right? So if I go back to my image over here, what is the period of that curve? Who can tell me on this Wednesday morning? Who can tell me? What is the value of the period of that curve? Yes. Oh, contributing already. Haven't even got the books out. I love it.
2.
Correct. All right. So 2. And I argue with people about this on YouTube all the time. What is half the period? 1. People go, Professor, you have made a mistake. The period is 2. I'm like, yes, I know that. Half the period is 1. And then you put that into the formula, right? So we're interested in the period, but really from a computational point of view, it's half the period that we're interested in. Okay? All right. Okay, so period 2L, not L, 2L, where L is some number, right? This, my friends, is a Fourier series. Okay, so this is quite triggering at 9 o'clock in the morning. Okay, so it's a sum involving cosines and sines. Okay, and if you look in that formula, we don't have 2L in there, we've just got L. All right, so let's just think back to school. Were they good times for you? Oh, we can talk about that later in the break, right? But what do we know? What are some series that we've known before? What are some examples of series that you've seen either at school or in first year?
The Taylor series, I think.
Taylor series is good, and Maclaurin series, right? So we know from Math 1231, Math 1241, Taylor series, Maclaurin series. What about if we go back to school, way back? What's a series that you see at school? It's not a trick question. Yeah, you do see that. I guess as a sum, that's more like a sequence, I would say. But you can sum it.
Is it wrong to say like AP and GPs?
Yeah, they're okay. Yeah, because we do want to calculate this sum. I'm even thinking like just geometric series, right? Geometric series. So for example, that. Yeah. Does that ring any bells? So geometric series, Taylor series involves derivatives, and it gives you an approximation to a function near a point. Let me say that again, right? Because this is important. For these ones, even if you can't remember how to calculate them, which is fine, I'm not expecting you to do that, they give you an approximation to a function, but only near one point. Okay? So let's go back to our Fourier series. What can Fourier series do that Maclaurin series cannot do? Okay, check it out. Is that approximation only near one point, or is it everywhere? It's everywhere. It's everywhere. So this is one thing that these Fourier series can do that the stuff that you learn at school and first year cannot do. So Fourier series are really good at approximating over intervals or the half line or whatever, right? Taylor series are terrible. Maclaurin series are terrible. They're good near a point. So Maclaurin series are good near, say, x equals 0, no worries. But as soon as you move away from that point, problems happen. You lose the connection. Fourier series are great. Okay? Fourier series are great. So, this is a mess. Now, oh yes, question. Hang on. Let me come to you. It's all part of the 5-star service. Yeah, that's all right. It doesn't matter.
Like with the first like music synthesizers, I feel like they use Fourier series, electronic music synthesizers.
They do. Yeah. So we know in music, right, you can use things like sawtooth waves, pulse waves, square waves, all sorts of things, right? And you're right, they're approximating them and making sounds with these Fourier series, Fourier representations. You're absolutely right. So that's another nice application, okay? All right, so that is a beast, okay? What does the S mean? I guess sum or something, right? Do you need to remember that for the exam? 9. It will be given to you. Okay, so you don't need to know it. So what's the A naught, the AN and the BN? They are numbers, okay? Or sequences, really, sequences of numbers. So if I push that up there, you'll see these are the suggested forms for they're called the Fourier coefficients. So what does this look like? What does this look like? Well, we've seen it visually, but let's just see what this thing looks like. So you can see down here, these things are called the Fourier coefficients, right? They go in front of the cosine and the sine, okay? So it's quite, there's quite a lot going on there, but a good question is, well, how do we know that the A naught out the front, the B naught, the AN and the BN are all in that form, okay? So let me just derive this quickly for you. I don't think you'd be asked to do it, but it's still good to know where it comes from. So let me just derive this format here, and I'll leave the other ones for you to do. Okay? So, just push that up. All right, so I'm going to assume that some function of t, I was using x's before, but I'll just use t now. Sometimes I flip between the two. Okay? You can write it like this. So for n equals 1, that would be the term. So for n equals 2, that would be the term. Okay, so that's all the cosines. And then I can put in all the sines. Okay, so you can kind of see why we use the summation notation, because it gets big real quick and it gets messy real quick. Okay, so my claim is that this constant thing can be calculated from that formula. Okay? All right, so let's try that and see what happens. Okay? So if you consider the following, I'm going to multiply both sides and I'm going to integrate. So I'm going to multiply both sides by cosine k pi t on L and integrate. And I can also do the same with sine. So you do those calculations independently. And let's see what happens, okay? The simplest case, so basically I take that mess, I multiply by a cosine, and I do an integral. I multiply by a sine over here, and I do another integral, okay? Let's take the simplest case. What happens for k equals 0 in the bottom line, okay? What do these things simplify to for k equals 0? If you plugged in k equals 0, what are those two integrals going to give you?
F of t for the cos t and 0 for the sine t?
Exactly. It's not a trick question. Okay? So if we just take the simplest case, right? So here it's like k equals 0, 1, 2, da, da, da. Okay? Let's take the simplest case. That's going to become 1, and then we get the integral of that, and that's going to become 0. Okay, now if I integrate here, I'm going to get the following. Right? So now I'm integrating this mess here. Okay, now all of these are going to be 0, right? Okay, so when you have a periodic function and you're integrating from, say, negative L to positive L, the integral is going to cancel out, right? When you multiply through by cosine. So you're going to get a lot of zeros here. Okay? So if we just move this over here, that's what you get. Okay? So you can do this for, arbitrary values of k, but k equals 0 is the simplest one. Okay? So that's where the first coefficient in the formula, A0 up the top, comes from. Okay? With the second, with the general case, it's a little bit of sort of in-depth integration, but you can still get it to work. Okay? So, similarly, Okay? So I won't do that. You can look that up if you want. All right. So what have we sort of learnt so far? Fourier series can be used to, this is one of the aims, to approximate things that are periodic. We can use them to approximate things that are discontinuous with a continuous function. We're going to use them to solve PDE, partial differential equations. And the form is, this is the general form, okay? In order to compute that, we want this coefficient, and this coefficient, and they're derived through integration. All right, so let's go a little bit deeper into this, because I don't want to go too slow, right? In this function on the screen that I'm showing you now, is that function even or odd? Think back to first year. It's even, exactly, right? So how do we define an even function? If you're explaining this to your mate, what is an even function? Yes, hang on, I'll come up. It's a good way to get my steps up, right? Yesterday I had like 120 active minutes. It's good. I like walking around. It's called active teaching. Yeah, tell me about it.
The graph is the same for both negative and positive values.
Okay, yep, algebraically that's correct. How would we do it visually? What's happening visually with an even function? So you're right.
I mean, it's if you y-axis, then it mirrors, right?
Yeah. Yep, you can think of a line of symmetry in the vertical y-axis, right? Okay, what happens if I change my graph and I'll do just x? Okay, is that an even function? No. How would you describe it? It's odd, right? But what do we mean when we say an odd function? How would you describe it? Exactly. So that's algebraic way of doing it, which is fine.
You can rotate it about. Yeah. You can rotate it about the origin.
Yep. So exactly. So the way I remember odd functions, you need the algebraic definition sometimes, but you know, I do this in first year. Okay, you got the pink function. I rotate everything 90 degrees. Oh my God, it's still the same, right? It's still the same graph. You just relabel the axes. Okay, that's an odd function. Okay? All right, so what happens with these integrals when f is even or odd? Do they simplify? If so, how? First of all, let's go back to basics. Cosine. Is it an odd or an even function? Even. Sine? Odd. Okay, so FOD. If f is odd, what does this mean for our, let me see if I can still get those formulas. What does this mean for our formulas for the coefficients? What does it mean? Well, let's look at A naught. What will the value of A naught be if F's odd? Have a look at the picture on the, I mean, you can't see this at home. Have a look at the picture on the graph if you can't, if you're not sure. What would A naught be if you've got the graph that's on the right-hand screen at the moment?
A naught would be 0.
Mm-hmm.
With the sine one, I think it'd also be 0 because you got an odd function. Oh, no, that'd be odd and even sign.
Yeah. It's all right. Let's just start with A naught. So this bit gives us the area under the curve, right? So if I'm over here, for everyone at home, and I want the area under the blue curve between -1 and +1, say, aren't the areas going to cancel each other out? And you're going to get 0? Right? Okay. So what about A sub n? I've got an odd function times an even function. What is odd times even in terms of functions? It's odd. So it's the same situation. You got area above the axis, area below the axis, and they're going to cancel each other out. Okay? What about the B sub n's? Okay, so we're still in the world where f is odd. So you've got an odd function times an even function. What is odd times even? No. These two situations, if they were all 0, we'd be in trouble, right? We'd have a 0 approximation. Even, exactly, right? If it's not odd, it's got to be even or neither, right? So, in this case, what does this simplify to? It'll be twice the integral from 0 to L. Okay? So why is that important? Well, 0 is usually a simple number. So, that's a shortcut, basically. So if we were doing the one on screen, which I'll put up for everyone at home, if we were working here, we wouldn't integrate over the whole interval from -1 to 1. We just go from 0 to 1 and multiply the integral by 2. Okay? That's what you would do. All right? Now, what's the other case? When f is not odd, it's even. Okay. So, if f is even, what is the A naught going to simplify to? F is even now. So let me change that graph. So I'll just, for everyone at home, I'll put this up in a second. Okay. So if you're computing A sub naught, how can we simplify that? I mean, it's a triangle, so you can simplify it anyway. But from an integral perspective, how can we simplify? How can we simplify? What can we do to our integral to simplify it?
Is it like the same thing as what we just did, which is double just from 0 to L?
Exactly. We're going to double the integral from 0 to L. Okay? So basically, you know that area and that area are the same, so let's just integrate over here and multiply by 2. Okay? So it's going to be 2 times this. Now, so when I put in the 2 down the bottom will cancel out. Okay, what about the other bits? Okay, so remember f is even here. So if I've got even times even, what does that give me? Even times even. Any idea? I'm probably going to get zeros, right? Based on what I did in the previous thing, right? So okay, hopefully I've squashed that all in there. So the point I'm trying to make is that when we are calculating these Fourier series and the coefficients, integration's a big step. But you want to simplify the integration as much as possible. Okay? You can do that using odd and even functions. Okay? Many, many times, right? But let's actually see where this doesn't work. So I'll put this up for everyone at home. I'll put it. Okay. Let's have a look at this graph now. Is the graph periodic? Yes? Can you just copy and paste and it looks the same? Yep. Is the graph odd or even? It's not, right? So that's a case where you can't simplify things, but the nice thing is it's 0 for part of the interval, right? So that's actually the only thing with it that you can simplify. Okay? So yeah. That is the only kind of nice thing out of that one. All right, questions so far. What's happening at home? People got questions? Yeah, that's it. Zach? Yeah, you rule. Yeah, exactly. You know your integrals. Let's just move this and do camera control. Get the focus off me. Still calling. Okay, so questions? Questions? We haven't done anything yet in terms of calculation, but we will. Okay? But this is the aim. The aim is to take a function that is discontinuous but periodic and approximate it over an interval well. Why would we want to do that? Because we're going to do that when we solve partial differential equations. Okay? That's the main motivation. All right? Questions? Questions? So, the main work with these kind of problems is actually computing the coefficients, the A0, the AN, and the BN. That's it. That's what you'll do, and then maybe we'll do something with it later. Okay? All right, so let's actually look at an example and see how we go. All right. Oh, it looks a bit blurry, right? Come back. Oh, it's a bit better. Okay. This is a super simple example, and it's going to be a square wave, basically. Okay? So we're asked to calculate the Fourier series of this function here. Okay, now the function is periodic, that's what this means, algebraically. The period is 2L, which is going to be 2 pi here. So the first thing I notice, half the period is going to be pi. So that, I need that for my formulae, right? Let's draw the curve. Sometimes they ask you to sketch the curve. So let's have a look. Okay, it's 1 on this interval, -1 on this interval, and it's 0 at the sort of the other points. So okay, that's my basic building block for the whole of the graph. Okay? So if I was to copy and paste that little sketch, I can do that to show the periodicity in a graph, right? So if I was doing that, I'd go, okay, well, let's take that and it'll look something like that, okay? Yep. Now, the function doesn't have to be defined at all points. You can have points missing. That's fine. The Fourier series just doesn't care, okay? All right. So is this function between negative pi and positive pi, is it odd or even? It's not even. What's the other option? It's odd. Yeah, not a trick question, right? It is say okay. So what does that mean? It means that these Fourier coefficients are going to massively simplify. Okay? They're going to massively simplify, which is a good thing. So let's go back, have a look at the case down here where I have an odd function. Okay, 2 of the coefficients are 0. That's nice. And 1 of the coefficients is just given by this integral. Okay, so let's try it. So in this case, A naughts and the ANs are all 0. All right, so our BN is going to be twice times this. So if I go here, this is what I want. Okay, in this case, L equals pi, so the L and the pi are going to cancel out, which is nice. Okay, so now What is f of t for t between 0 and pi? What is f of t for t between 0 and pi? Who can tell me? I've drawn it in the graph. I've stated it as the function. It's 1, exactly. Okay, so you go, okay, this is my interval of interest. From 0 to pi, the function's just 1. So all I have to do now is integrate sine of nt with respect to t. And imagine n's a constant. So let's do that. Sine's going to become negative cosine. And I'm going to divide by n. Okay, it looks like I'm making progress. Let's put in t equals pi and t equals 1. And I'll bring that negative out the front. Okay, cos of 0 is 1. Okay, that is our Fourier coefficient for n equals 1, 2, 3, 4, 5, 6, 7, 8. Okay? All right. So, what does our series look like? I'll leave that with you. We'll come back to that in 10 minutes. Okay? Very exciting in the break. Let's get back to our Fourier series. Now, let's just remember where we are. Fourier series are used to approximate these discontinuous periodic functions. Here is an example, a super simple example of a periodic function that has a few jumps. This is also an even function between negative pi and positive pi. Okay? That means that all of these Fourier coefficients get massively simplified because areas cancel out, right? So the question is, what does this look like for this particular problem? Well, that's going to be 0. That's going to be 0. That's going to be something that we just calculated. So this whole series that we're calculating now is not going to have any cosines in it. It's only going to have sines. Okay, the sine functions added together. So it's sort of like a half a series of what this general form is. Okay, so let's play a little game. Cos n pi for n equals 1, 2, 3. How can we simplify cos of n pi? So cos of pi, cos of 2 pi, cos of 3 pi, cos of 4 pi, cos of 5 pi, cos of 6 pi, cos of 7 pi. Okay? Can we simplify that? That format is good enough, but it's still not as simple as we can make it. So let me go back to GeoGebra. Okay. Here we are. So I've just put in cos of x pi. So when x equals 1, what's the value of the function in that graph? X equals 1. It's not a trick question. When x equals 1, negative 1. Okay. When x equals 2, what's the value? Positive 1. When x equals 3, negative 1. When x equals 4, positive 1. Can you see there's like a pattern? right? It goes, you know, negative, positive, blah, 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 right? Okay, so we can use that to simplify our expression down here. Okay? So let me simplify this. By making that. Now, why would you want to do that? Well, you can see cos n pi is either positive 1 or negative 1. If it's positive 1, the thing in the square brackets is 0. Right? If this is 1 and I'm taking 1 away, this is going to be 0. If this is negative 1, I'm going to get negative 2. Right? So let's have a look. What's going to happen? It depends on whether n is odd or even. Okay? All right, well, what happens if n is even? That's going to be 1 minus 1. And for n odd, this is going to become negative 2 in here. The whole thing will be negative 2. Okay? So, now we can actually write out our series. We've simplified it as much as we can, and we get something that, 4 on n pi is not bad. But let's actually write out our series and see what happens. Okay, so we can go back to this general form. We know that's going to be 0, that's going to be 0, and I'm left with this sum of sines. Sorry, AN. Okay. So that's 0, and this is going to be this thing. Okay. So the BNs, you can write it like this, or you can write it like this, or you can write it like this. Okay, so I'm gonna choose this one here. So I'll take the negative sign out and put it in there. Okay. And so now I'll simplify this by only adding the odd ones. So why am I only interested in the odd values here? Because everything else just gives you 0. So I can do this. Okay, notice how I've changed the upper and lower parts of the summation sign. I'm now saying n's odd, so n's 1, 3, 5, 7, 9, right? If you don't like that notation, you can also write it out like this. Okay, so they're all the forms that I can think of. They're all the forms that I can think of. Now, depending on what you like, you can use some of those forms, one of those forms, but at the end of the day, whatever form you use, the series should look the same. If you're ever worried about it, and I do this all the time, I write out some of the terms. Okay, so let's just write out some of the terms and see what happens. So let's start. I'll start with this one, right? Okay. Let's put in k equals 1. It'll be 4 on 1 times pi times sine of t, right? Okay, let's move along. Let's put in k equals 2. So it's going to be 4 on 3 times pi times sine of 3. Sine of 3t. Let's put in k equals 5. 4 on 9 pi times sine of k equals 1, 3, 5. Yeah. So I've done 1, oh no, 2, 3. Sorry, let's put in k equals 3. So I'll get 4 on 5 times pi times that. Okay? So if you're ever confused about the notation and you're discussing it with a friend or chat GPT or ask Eric, the bottom series is the one that doesn't change. The bottom series is always the same, but you can just write it in various equivalent forms using the summation, the sigma notation. Okay? Questions? Questions? So, who can explain what I've done from here to here? In this step, who can explain? Because this, last time I taught this course was a long time ago, but I still remember that students get triggered by this. So what is going on from that sum involving nod, or n odd, to the other sum? What have I done? What have I done? Who can explain it? Anyone on this side who can explain it to save me walking over there? What have I done? Okay, I'm getting my steps up. I've already walked about 5k, so that's good.
So essentially, we changed our sequence of your numbers, like 1, 2, 3, 4, so on. You force it to be odd by multiplying it by 2, which gives you an even number, and then you minus 1 to force it to be odd.
Yeah. Yeah, so you don't have to use any of these things. Sometimes this is super useful. So when I say n odd, I mean n equals 1, 3, 5, 7, whatever. Okay, you could write that as well. It's up to you. It's up to you. Okay? Questions?
Would it be possible to make a sum to infinity from this one, or to make a sum to infinity for this one?
Yeah. So we can use these kinds of series to also learn about infinite sums, right? So if you look on the next slide, on the next one, this is what you're talking about, right? Is that what you're talking about? So, if you have this format and you sub in a value for t, then that'll just give you the sum of something and it will be some number, right? So in fact, Fourier series also helps us understand infinite sums of just regular numbers, right? So yeah. Other questions? Other questions? Questions at home? keep it going. I love Fourier series served with brain rot. I will try to do that. I love it. Okay. So, questions. The formats can change. So, this, they can all change. But the bottom line is actually, you can't change that.
Quick question regarding the original function that we had with absolute x plus x. Is it possible to, like, instead of taking...
Yeah, let me put it on the screen. Are we talking about this?
Yeah, that's the one. Instead of taking like, if you had a Fourier transform of the sum of two functions, can you just individually Fourier transform the functions and then put them together?
Yeah. So yeah, it's a good question. So the question is, as far as I'm aware, if you have two functions, right, and they sum or whatever to make a new function, and you want the Fourier series of the new function, can you just take the Fourier series of the parts and then add it together? Yes. Yes. So if you have, let's say, let's say you have, okay. All right. Oh, actually, let's do... Yeah, this is better. Okay. Actually, let's make that even better. Okay. So, you look at this function. It's not odd, right? It's not an odd function. Would you agree? Yeah? But can I make it an odd function somehow by doing something to it? What can we do? Yeah, shift it down 2 units. Okay? Shift it down 2 units. So, if I have this original function and I shift it down 2 units. Boom. So, to do that, what I would do, I would just take the Fourier transform of that function, which is odd, and is easy to calculate, and then I take the transform and add 2 units to it. The series, and the Fourier series, and add 2 units to it. That's it. Work smarter, not harder, right? That's what I would do. That's what I would do. Other questions? I mean, the main thing with these problems, right? It's just time. And you want to save yourself as much time as possible. So why calculate 3 things when you only need 1? Or 2. Sometimes you only need 2 things here. Okay?
What does the ft plus 2 pi actually mean? In the question.
Oh, yeah. So, yeah, good question. So, this tells us that f is a periodic. This is the algebraic way of saying, hey, f repeats, and the period is that thing, whatever that is. So if it was, say, f of t equals f of t plus 3, right? The period in this case would be 3, units. Okay, so every 3 units you get the repetition. Other questions? Okay, so the thing that students find bizarre about this stuff is this function is not a complicated function. Right? Would you agree? This is not a complicated function. This is crazy. So it's like we're taking something super simple and we're making it super crazy. But there is a point to it, okay? There is a point to it. So so now we've calculated something. Let's go through and have a look at what we produced. Okay? So I've just used Maple to plot this, and let's just draw in the original function. Okay? Let's just draw in the original function. So it's boom, 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 boom. Okay, so you can kind of see from the picture, I think of the red curve as like a wire, and you're wrapping it around something. But what do you notice at the edge points, say, t equals pi, t equals 0? What is that wire doing? What is that red graph doing? That's the first 10 parts of our Fourier series. You can't plot the whole thing, but what does it look like the wire or that red curve is doing? And it's sort of oscillating a bit, right? But what about what's happening here? It looks like it's got some horns. What is it doing there? What does it look like it's doing? This is a pretty important phenomena, right? What does it look like it's doing? Yes?
I mean, I'm not exactly sure what it looks like it's doing, but I think that the area under the actual graph looks roughly equivalent to the area above it, so that it would be accurate in like integration.
I'm not really thinking about area here, but that's good to consider too. What is it like? Let's go in. Would you say it's a better approximation there than it is there? Right? And there versus there versus there. Why is there a gap? Why does it sort of have a nice tight sort of wrap and then deviates a bit?
Definitely not a mathematical explanation, but like how I see it in as a phenomenon is that like it's trying to prepare itself for like the big jump or the big like drop sort of idea.
Yeah, that's it. So you think about this little red curve. It's got to do a lot. Okay, it's got to do a lot. It's got to wrap itself around this thing and then make a jump super quickly, right? And it's still got to be continuous, and it's still got to be differentiable, right? That is hard for a function to do. So so you're absolutely right. It has to sort of get ready. It's like, oh, I'm going to do something. What? Right? You got to sort of jump up before you jump down, if that makes sense.
So it would be more accurate along long continuous areas then? It would be more, it would be less jumpy if you've got a long continuous graph compared to that?
Well, it'll still jump. It'll still jump. And I guess how much of a jump. If it's more about the the magnitude of the jump than the length of the interval. I think that's another way. Like, I'm sort of taking your idea and flipping it a little bit. Yeah? Okay. All right. So, what else do you notice? What else do you notice? Here, the red curve and the value of our original function are exactly the same. Okay? So, let me just put that back up. Let's see if I can do this. Yep. You can see here, at x equals pi, the original function is 0. At x equals pi, the Fourier, this approximation is also 0. Okay? It's also 0. So at that point, it's exact. It's not approximating anything. It's exactly the value of the function. All right? What else can we talk about? Well, let's have a look at this box down here. Okay, so what does this box say? Integration is your best friend, okay? And if you can simplify the integration, that's brilliant. You don't want to be computing things that are 0, right? Now, the second part have to do with continuity. If S is continuous at a point, then the Fourier series value at that point is equal to the original function. Let me say that again, because you're going to use that at some point, right? If you have a continuous curve to start with, right, then the Fourier series and the curve is exactly the same. If the original function that you're trying to approximate or trying to describe has a jump discontinuity, like those things, okay, then the value of the Fourier series at that point of discontinuity is this. It's the average of the two limits, right? So okay, so let's have a look at our picture and see if this makes sense. All right, so let's come in here, and this will be our point, C. As we come in from the left, what value is the black curve approaching? As we approach that point from the left, what value is the black curve, our original function? What is it approaching? 1. Positive 1. What about if we come in from the right? Negative 1. What's the sum of those two things? 0. So it's basically the average, right? This says it's the average of that limit and that limit. In this case, it's just 0. Okay? So we're going to use that. That's called Fourier's theorem down the bottom. That's going to be super helpful for all sorts of stuff. Okay? Questions? Comments? We've computed our first Fourier series. Congratulations. Right? Now the question is, what can we do with it? Right? What can we do with it? So has anybody seen Fourier series before? Oh, where have you seen them? Oh, so how do they teach it in that? Hang on, I want to put... No, I think it is. Yeah. So what can you remember, a setting or an application, or are you approximating signals?
Yeah, so we were told we can approximate square signals with the Fourier series, which is what just did in the example here.
Exactly. So square waves, sawtooth waves, you know, all sorts of stuff. The most important thing is the function that you start with, that you want to approximate, it's got to be periodic, right? Otherwise the cosines and the sines don't work, right? That's the most important thing. Okay? Well, for a transform, no. We're not doing that. No, we're not doing that. You might see that, if you do some more maths, you might see that in third year. Yeah, because you really need to know complex analysis for that. And this course is already full of stuff. So. All right, so just to remind everyone, you know, let's say we had a curve like this. Let me put that on both things. So these are your approximations. Pretty cool. Pretty cool. Okay? Pretty cool. Better than Taylor, better than Maclaurin, but probably harder to calculate. All right, so let's have a look at the second part of this question down the bottom. Okay, there's a quick way and a slow way to solve this problem. Okay, so you want to really get out the strategies when you're looking at these things. All right, calculate the Fourier series of this function. Okay, so I'm just going to put that in on this picture. Oh, I can't do that. Oh yeah, hang on, maybe I can. No, I can't. All right. No, I can't do it. All right, so let's just draw a little picture. It's 0 for t between 0 and 1, and then it's 1 here and 0 here, sorry. So let's draw a little picture. Okay, so... All right, so it's 1 here, and it's 0 here. Okay? So that's our function. Now, notice our function isn't defined at all the points in that interval. It doesn't matter. If you're missing a few points, it doesn't matter, right? So that's that. That's that. Now, it's periodic. We're told the period is 2. So we would copy what we see in front of us on the graph, we would move and we would paste. Okay? All right. So there is a fast way and a slow way of doing this problem. Who can suggest a strategy to simplify the situation?
Oh, it's almost an odd function, so you just like bring it down half a unit.
Mm-hmm. Yep. Bring it down half a unit. Shift it down. Okay? So we would take that and just shift it down half a unit, and whatever, you know, that'll be the Fourier series for it, and then you shift it back up by adding 1/2 into the answer. Okay? So that can save you bucket loads of time. Yeah? So I would, if I was doing this one, I would say, okay, g of t, I'm going to introduce a new function. It's going to be f of t minus 1/2. And I compute the Fourier series of g, and then I'll shift everything back. Okay? So if I shift everything, g is odd. So what do I know about odd things? That's going to be 0, that's going to be 0, and that's going to be that. Okay? So Okay. And also, this is going to be twice. Okay. So in this case, L is going to be 1 because we define L to be half the period, and G is going to have the same period, right? So nothing to worry about there. So let's plug this all in. Okay, G of t between 0 and 1 is going to be a half. Okay, so now we're just integrating a half of sine n pi t. Okay. So the 2 and the 2 are going to cancel out. I'm going to integrate sine to get something like negative cosine, and I'm going to divide by the n pi. Okay, so I know when I put in t equals 0, this is going to simplify to 1. When I put in t equals 1, I'm going to get my old friend, cos n pi. Okay, so how can we simplify this? Goes back to our ideas that we looked at before. Cos n pi, where n's an integer. Cos n pi, n equals 1, 2, 3, 4. What is it? How can I simplify that? Any ideas? We just did this in a previous example. Any ideas? Come on, people. Yeah, it's either going to be, this is either going to be positive 1 or negative 1. Yeah? So, if this is positive 1, the whole thing's 0. If this is negative 1, I'm going to get negative 2, right? All right? So, my ANs are 0, my A naught's 0, and my BN is this, depending on whether n's odd or even. So what is our Fourier series? Okay, my Fourier series for my original function is going to be that plus a half, so I'm sort of shifting everything back. Okay, so BN's that, depending on whether n's odd or even. So we can simplify it down to that. I think I've just shoved it in. It's the same as this one. Okay. So that's another good example where you can save lots of time by just moving things around. Okay? Questions? Comments?